Morning, everybody. Can you guys hear us? Yes? Thumbs up if you can hear us. We're gonna get started. I'm gonna be in this smaller room. I like this room because it kind of you can see everyone, and we'll start doing lots of brainstorming and things like that. So it's just we'll try jamming, even though you feel crowded, it's more fun. We're gonna start by we happen to have a quick visitor here. Uh, had a pretty cool paper come out last week on mimicking or building, I don't like the word mimic, building an analogy to kind of camouflage of how materials change color. So I'm going to try to do or show a quick demo. You should do a demo for the class. While Enrico, let's pull out a video online. Yeah, so we could be tight. You type here, so we can show a video for everyone. Just open one of the browsers. And again, sort of in a flavor of the types of things we want to do are much more show and tell. So anytime you're all working on something. And
Hello, Manu.
Vaibhav, can you hear us?
Yeah, your
Yeah.
voice is a bit muffled. Maybe you can use the laptop which is closer to you.
Oh, that's a good idea. I'm gonna use my Zoom. Okay. Yeah. Yet. So I'm gonna connect. So you can unmute yourself. Okay. Okay, so just share your screen. And then Siddharth, you should walk through that video. It's way too, I think. We already got started. Come on quickly. So let's play that video for a second. We're just gonna watch this video for a second, and this has audio? No. This has audio. Okay. If it has audio, we can just listen to it for 10 seconds. So.
And texture before returning to its original state, inspired by shape-changing octopus camouflage. Some cephalopods, like octopuses, can change the texture and color of their skin. Muscle fibers transform their skin from smooth to rough, while chromatophores, cells filled with pigment, allow them to change color, making for a sophisticated, shifting camouflage. Scientists have developed lots of ways to control the color of the material, but dynamic control of the visual texture of an object, how rough or glossy it appears to the eye, has proven trickier to crack. Now, though, these researchers have developed thin polymer films that can be programmed to produce different textures or colors when exposed to a fluid. Using a beam of electrons, the team can draw a design on the surface of the polymer. Then they add water, which causes the polymer film to swell. The areas exposed to the electron beam swell less than the rest of the surface, so complex topographies can emerge in a swollen state. And by depositing a 20 nanometer layer of metal on top, they make this textured surface more reflective, so easier to see with the naked eye. To control color, the team sandwiched the polymer between two thin metallic layers, creating something called a Fabry-Perot resonator. This creates a surface that changes color as the polymer swells, with different swelling in different areas, creating patterns and contrast. By combining these techniques on either side of a thin, clear layer, the team can control color and texture in the same film. And by adding solvents or drying the film out, they can reverse the transformation. The researchers say this tunable photonic skin could be used in wearable devices or soft robots, so long as they don't lose sight of it.
That's all. It's like 5. So could you all hear that? I'm connected on Zoom. Oh, yeah, I'm connected on Zoom. Could you all hear me now? Okay. So Sid happens to have this material. Have him show, just do a quick demo for it, and then we're going to transition to the topic for the class today. And then lots of questions people have questions about what's the use and application, and I'm going to answer it in a very simple way in a second. But let's just watch the demo first. You guys have to actually see it. So get in there, kind of show that you're surprised. Remember, I said 6 years of work. So you gotta be excited. Okay.
Pressure on the reaction.
Yes.
A little second, maybe. Yeah, so this is a physical sample of the skin that we were looking at, where we've made using the semiconductor tools that we talked about downstairs in this building. A layer of polymer between two layers of metal, and we control how much it swells when we add water. As you can see right now, when it's mostly dry, the color is the same everywhere.
Oh, I just made it wet now.
Oh, that's good.
It's already started. The reaction has started. So come on, take a look. Can you guys watch the change color in real time? You have to get in there. So based on the angle that you're looking at, otherwise you can't see it. Maybe we'll do it one more time on the screen. Yeah.
Even take this off. And so right now it has like a certain color. It's kind of orangey. You probably can't see too well besides that. But now I'll take it off. And the parts which were like yellow and green, the pattern which maybe you can see right now, will slowly start to disappear. And it will all become just like pink uniform, and you can watch that for the time. So that's actually maybe easier to see.
Okay, and then I'm gonna do a quick demo here. Let's see, I think how good the camera focus are. So first of all, you're all looking at a piece of silicon, right? This all our transistors are made out of. It doesn't have to be silicon in any way and form. It just this is convenient in the fab. There's one thin film of gold, another film of polymer, and another film of gold. It's actually pretty simple. And then if you notice, I'm going to bring it here. You start, it's not focused anymore, but you see the red region, and then you see the colorful region. That's where the water is. So anywhere there is moisture, the polymer film is swelling and it's changing the color. And it's a little bit like, when you notice sometimes oil spills on, say, a road that you're driving, you see all these rainbow colors appear. I mean, to a certain extent, there is a cavity that's forming between the two. But now, kind of the context is that you can do this by design. And the coolest part is that hidden inside, there is also a pattern that how much the polymer will swell somewhere is dependent on what has been written as a pattern on it. So if Sid wanted, he could have had his name appear in secret because there was hidden, the electron beam had changed the polymer on the surface, and that would have changed exactly where that swelling would occur. And the beauty of much of this is if you think about incredible number of things in nature change color. Very few things in our life change color. I do know there is a car now that can change color, the photochromic. I think it uses a thermal sort of a heat as a mechanism. And then I'll answer the brief question. So this was just a fun, cool demo because Sid is heading out to Caltech. So I was just meeting him a few minutes before. But it brought up a very interesting point. What is it good for? Sometimes I think the purpose of this class is twofold. You need to understand the physical basis of our world so you can do cool things. Understand what is possible. And then in the other part of your brain, you're thinking about what are the most important things we need to be solving as problems. But it doesn't happen at the same time. So you keep two of these seeds running, and then there is a moment, aha moment happens like, oh my God, this problem that I've been thinking about for the last 30 years, wait a second, this clever, simple physical principle has a solution hidden inside it. And that's the art. So there's no prescriptive nature to any of this. So you should just be excited about it. And the simplest answer of why do this is because it's cool. I want to wear a jacket that can change color so I don't have to worry about any room I go in, it'll be fashionable. That would be fun, right? But at that same time, now you can think about this. It's like, okay, let's ask ourselves a question. These things are changing colors and patterns dynamically. If you ask yourself, somebody has heard of this idea of how roofs are painted in certain sets of colors to make them cooler. There's different parts of the world that are actually using the color of the roof as a mechanism to bounce back all the light in a building so that the building passively remains cool because color absorbs. So you can start things like, oh, wait a second, I now have a context between color and temperature. You might be thinking in the context of diagnostics. There is a lot of times that we use very complicated mechanisms to bring different colors of light to a sample. I mean, in this sense, it's actually suddenly creating a type of cavity that would create different wavelengths of light in a totally different way. So I think it's not, you don't always start with this perspective. I think you have to have a very strong perspective of the problem that you care about, but you have to show interest in every possible new thing, especially when it's done simply. Although the techniques right now Sid's been working on are complex, take time in that space, but this seems pretty straightforward. There would be analogies to this that you could literally make this for sense. So, that would be fairly straightforward. And that's why the mechanism is interesting. It's just basically two gold reflectors with something that swells. Almost all polymers have some swelling potential because they're going to bind to water in some way, so it's quite simple. And then you guys can all think in your own head what you might want to use this for. Yeah, the process is totally reversible, which is also cool that it returns back to the exact same configuration to begin with. But I think this is a good lesson for the class in general, that there are certain, the title of this class is you want to learn kind of technical space of how to build things and physical phenomena that are often present but are not in control. These things you see often enough, but you don't physically control. So now this brings a step of control. And at that same time, you're quite excited about different applications, but the convergence of that is non-trivial, and the convergence of that happens in your head, and it doesn't happen on the first day. It's so you have to build a cache register or history of lots and lots of mechanisms and physical mechanisms that you could utilize. Another fun one would be is I know there's a huge issue right now in fake medicine. So across the world right now, when you take a pill, there is a significant chance that what you're taking is not what it is. Classic example for lots of malaria medication. And the packaging is exactly the same because the machines that make packaging people have figured out. So there are massive fake businesses out there, and it's quite dangerous if you give that to a patient. And so a lot of people have been thinking about low-cost ways of testing drugs right then and there. But another thing you could think about, could you hide something in the capsule that you know is simple to implement, but is not something that would be implementable by somebody who's hijacked this process? Packaging is super simple. So, there's all this holography that's printed. Anybody can make holography now because we have moved towards making holography. So you can imagine, is there a way that I would create this color code? So before you take the pill, you dip it in water. If you saw a code appear, then it means it's legitimate. If it didn't appear, that's, I'm making this up. But you can start imagining suddenly it's like, encoding information in systems in different ways that doesn't change the cost of the pill, might help you figure out a class of a solution. Okay, so I'm going to say bye to you. I will catch up. Send me a message. We can do a Zoom call and a longer chat. Say hi to John. I haven't seen him for a very long while. And then we'll stay in touch. Sid and I wrote a paper together in the COVID times. That's how I knew he was a first-year grad student. Actually, you should say a word about that paper. What did we write the paper about?
At the time, there was a huge shortage of N95 masks in various areas, and people were exploring how you can reuse them, but you want them to be decontaminated before that. You can do that with UVC and many methods that you can find in the US. But one question we were thinking about, what can we do if you're in the middle of nowhere in a very low resource environment, but you still need to, you have actually maybe a greater need to reuse the masks. So something that they have in those settings is everyone has a pressure cooker. Everyone uses that to heat water. So we were kind of investigating, can you use boiled water from a pressure cooker to provide similar sort of reuse characteristics as much more complex methods. So that was in my, I did that in my kitchen, and then Manu was kind enough to provide parts of his lab for the airflow filtration testing to see how well it worked. So yeah, that was a really fun project, literally when nothing was open. And yeah, it got me started, I'd say, about thinking about lots of different things. So
Yeah, no, I mean, I think that was the first Frugal Science project that we did together with Sid. I mean, I think one of the things to think a little bit about is sometime there was the need to do things was quite urgent. We were getting calls every single day. We have collaborators across the world. This was in Bangladesh. N95 masks can cost multiple dollars, and you get one per year. It's like, this is your quota of a mask. It's like, I mean, so now we, at that COVID time in here, we were starting to think about, because there was a mask shortage, when we talked to many of our, I mean, and TB is a huge issue. So you need to protect yourself. And TB spreads through the air the same way as COVID, and has huge repercussions on people. And so in some sense, the need gets highlighted sometimes in a point of crisis, but actually that need still exists. And still, I mean, pressure cookers are used for sterilization as the most common method. Most I mean, not needles should not be, but syringes are actually also reused in that context to begin with. So there's a framework for thinking about sometimes that was a crazy, crazy time. And maybe at some point of time, we'll talk a little bit about COVID and other threats. Okay, I'm going to jump into the class. Good to see you. Yes.
I learned a lot about communication, but as Manu said, as you guys have this nugget in your mind now, and if you think of things like a smart tool or a build-in pooling that you want to talk about,
send Sid a message.
Email is very accessible. Maybe you can go in the chat or something, but I'm very accessible. Feel free to write to me.
Yeah, and I think one of the threads is we wrote people in, if there is a particular method we want to use, then you can always reach out to those people and say, hey, we want to use it for this, and then figure out whether that works. All right. Okay, so let's transition to what I want to cover today. I heard you guys, how many of you were able to make it for the Friday session? Okay, so a few of you know how to use a Foldscope. Yeah, what did you guys find? Yeah.
I thought it was really interesting that you could like connect, like use your phone as well to get even like a better view.
Yeah. Were you able to see something new that you haven't seen before? Yeah, did you guys get some samples? Because I heard Rocky has like an explosive sample. Yeah. Yeah. I mean, I have to say, I mean, I have been all throughout the weekend, I've just been imaging that sample. And I think one thread that I want to do is briefly cover a little bit of a historical background on Foldscope, because some of you have now seen it. If you haven't as yet seen it in your hand, we'll get a shipment out soon, so you'll get a chance. So for the next, how many minutes do we have?
I'll send it at 10:30.
Okay, so we still have 40 minutes. I think for the next maybe 20 minutes, I want to cover the history of Foldscope. It kind of, let's use it as a case study. It's a fun way, because I know every up and down in that project, and it'll kind of give you a sense of, there are two aspects that I want to cover. I want to cover a little bit of the technical aspects of the optics, but we will do an optics session starting Wednesday. So we'll dive into the theory, but I'm now leading with an application and then saying, oh, how the hell is it possible that I can get this kind of resolution, single bacterial imaging resolution at a price point of $1? Now that drives you to understand the physics behind it. Sometimes it's the other way around, where you say, oh, this physics is really cool. I'm going to now figure out what is it good for, or can I actually use it to build something? So this will be a little bit of a case study. And let's see if I can find old. It's hard to find an older deck. The older the deck is, the more history there might be in that deck. And unfortunately, okay, why don't we do this? Let me share my screen. So if I share my screen, I'm gonna play a video actually. It's kind of slightly embarrassing, but it has some of the older footage that I don't have. So we'll sort of the story begins for Foldscope is I'd started my lab in 2011, and one of the things that we had started was this premise that, it was very clear, and it's still true, that scientific instruments are not widely available. And I had taken a grad student of mine, who you will see show up in the screen in a second, to Thailand and India. We were working on malaria. We still work on malaria. And we were on the border town between Burma and Thailand, where there is a strain of malaria that's resistant to all drugs. And in there, in one of the clinics, and at that time I was thinking about malaria diagnostics. So it's kind of funny, full circle, that now we're using Foldscope for diagnostics. But the origin story of Foldscope was in diagnostics. We ended up building it then for education. And then last 6 months ago, we brought it back and actually built diagnostic applications back on it. So it's kind of this full circle. At that time, I visited a clinic, and I remember explicitly in that clinic, there's a whole bunch of microscopes, and I know many of you have had these experiences. It was actually a rabies clinic, which is even another problem that I'll just mention. So most of you know, if you get bitten by a dog that has rabies, it's a very critical time. So first of all, you should be careful. And most animals are not vaccinated around the world. And there is a really kind of, I would say, a lack of a better word, a very gory test that's done that I learned, that they literally have to look at the brain tissue, and there is a particular antibody that they have to look for rabies in that. So they kill the animal in the anticipation of even trying to figure out, and this is one of the standards. And so there was this fluorescence microscope in the middle of the jungle, and locked in, and it was a $150,000 microscope in the middle of nowhere. It was the most expensive thing that you would ever see. And it's sort of that image didn't fit, because, when you think about an object and you think about a middle of a jungle, and you say, oh, the entire infrastructure of this entire primary health center is less than the cost of this instrument, and all it was doing fluorescence microscopy. So that was sort of the starting point. It's like, can we do imaging, and especially high resolution imaging in the field? So that led to Foldscope, and I'm just going to play this video. Uh, the video was made 2 years ago by story of a golden goose. Some of you know that story. Anyway, a goose that lays golden eggs. And the golden goose is actually a really beautiful story, which is, it's a political story. There used to be a senator, I'm not going to name which political party, but you guys can guess, who started a program trying to shame scientists that, oh, look at these scientists, they're studying fruit flies, ha ha ha, or they're studying shrimps, ha ha ha, and not realizing that most of your drugs that come from is actually studying most of these basic animals. So that became this massive program. It's used every year. So if you're in that list, we've shown up in that list twice. You get bombarded by all these journalists making fun of your research and saying, oh, it's basically a mockery of basic science. That's the sad part of it. But then another congressman saw that, and he realized and saw the value of basic science. And I think, in the United States, that's been supported for the last 100 years. And then he started a second program, which is counteracting this program. That's the Golden Goose program, which is the idea that certain sets of ideas can sound silly when you say it first, but then they can have deep impact in our society. And something like this, it's like we're making octopus skin, and suddenly it turns out it's a wearable sensor that everybody is using for all kinds of things. So that's the context of it. And Foldscope got the Golden Goose Award because it sounds silly when you say we're going to make microscopes out of paper. And now there are 6 million of kids around the world using that as a tool. So I'll just play this video. It's embarrassing, but let's see what it has to say. All of this data is with the Foldscope. There's a little bit of an irony to this. All fun ideas start on a piece of paper. This one ended up remaining on paper.
That was really what part of our inspiration is to think about a microscope that could literally be $1 or less.
People found that silly, primarily because, of course, I said, oh, the right way to manufacture microscopes is out of paper. And that by itself was laughable. That was the grant that I wrote to the NSF. I was finally surprised that we were supported to pursue this idea of what I call print and fold optical instruments. When I started my lab, I spent some time in Thailand, India, South Asia, and experiencing and seeing the lack of capabilities that existed for lab technicians across the globe. Once you don't have the tools, no matter how dedicated or passionate you are in engaging with patients, you really cannot provide the best care. I remember being in Uganda talking to a person who had been training malaria microscopists for the last 40 years of his life. And he explicitly told me, Manu, you should come back to me when you can do diagnosis under a tree. Jim was a graduate student at that time, and I met him by a coincidence because he was looking for a lab to work in. By the way, the machine that you saw, I think his background showed that he cared deeply about people that I cared about, which is people that have very using that same.
When I met with Manu, we talked about, I think, 3 different ideas that he had. And the one that really, caught my attention was related to making a low-cost, version of a microscope using a ball lens. The same day that I met him, he just invited me to come in the lab and, just starts playing around with different things to get started. We just got some ball lenses. Your first thought of how to try to view something small through a ball lens is you just pick it up and you try to look. The first thing that goes wrong is that you end up poking yourself in the eye, right? Ultimately, where we made our big jump forward is when we found this source for black paper. It's a cardstock paper. The big step after that is really just to make the paper big enough so that it really gets your fingers out of the way of your eye. After that, it was just lots and lots of iterations and, brainstorming about different features.
A lot of people have told me I'm crazy. I think I do remember explicitly a time we wrote a paper, we figured out that it worked. The next day, Bill Gates tweeted about it. It's like, oh, a $1 microscope, interesting question mark. And it stuck with me. It's like, why did he add a question mark? Up till now, we had built 100 every time in batches, all done by hand. And then that day, the mission had changed. That tweet inspired me to flip that and said, we're going to make 10,000. And it turned out we overshot. We made 75,000 of them. And so then we chose another harder problem, which is we're going to make 100,000 of them. Then we made 1 million. And now at this very moment, we are actively thinking about how to manufacture 10 million of them. So we shipped the first. At this point, from the lab. We have made more number of microscopes than many 200-year-old companies in this space, primarily because accessibility is at the heart of what we do. Everybody deserves the right to explore science, no matter what your background is. Most important work really has happened in the community, which remains independent from the commercial entity because the community is driven by the community of users. There was a guy in Seattle who heard about Foldscope and decided to quit what he was doing. And he biked from Laos to Cambodia to Thailand, all across for the next year, running hundreds of Foldscope workshops. That's what he did. Everybody has an innate capacity to create knowledge.
When you share something with them that allows them to kind of see the same world they've always seen before, but in a new way, it can be very exciting.
So one of the things I'm going to do is true understanding of science comes from engaging in the process. And I very strongly feel we're just getting started. We truly have the capacity of bringing scientific literacy in a very physical way globally. That's Lebanon. So kind of that's the golden goose. And kind of the analogy to this to be thinking about is the idea that we don't choose applications for Foldscope. We build a platform and then we let other people build applications on top of it. And that's what's different about that project as compared to many other things that we do and things that we would do. It's not an either or that you have to sometimes be choosing a very particular thing that you're going to try to solve. You can also ask yourself a question, what is a fundamental capacity? So Raspberry Pi is a great example of that. People build Raspberry Pi. I mean, computers are a general good example of that you build that as a general purpose, low barrier platform and let other people take ownership of things that would build. So there's roughly around 1,500 papers written on Foldscope now, many of them in context of human diseases, animal diseases, thinking, I mean, of course, education is one of the biggest application that opened up in that space. There are detection for fake drugs done with something like this. There is many new species that have been discovered. That's what I was asking you if you guys started poking in, and I can guarantee you in that alpine pond are completely new species that have never been described. And this is a little bit ironic because you guys got to see it, but not realizing that you might be looking at something that nobody has looked before. That's kind of how rich the microscopic world is. And I'll show some videos and post them on Discord because I spent the whole weekend just doing that. And I already have maybe around 10, 15 things that I have never seen in my life, which is, I've done this for 15, 20 years now. And it's rare that it happens, but it does happen on a specific sample because just suddenly it's so rich. So I think there is this tension between thinking about trying to solve problems or building platforms. But then again, the key thread is it would not have had, this particular project would not have had the kind of impact if we had gone from $1 to $10. That's sort of the intuition to think. That's the intuition I have. We never did that experiment, but I know many efforts and things that have gone in. There was a transition point to ask that if you cut a certain barrier in terms of, so the design required that we put cost as a barrier first. So it's not random that I started thinking about these very high curvature lenses because high curvature lenses can be manufactured using a physics trick. And maybe I'll let you guys think about what is that physics trick. Let's take a quick break from the video. If I was to ask you, what is the most low cost way to manufacture a perfect sphere? How would you do it? You can just unmute your screens or how would you make a perfect sphere? Does anybody know how we make spheres? Sphere, like, a circle, but a three-dimensional circle. How would you make a perfect sphere? Let's come up with a few ideas. Some you already know. I bet you know some of them, and some of them are better than others. Yeah, go ahead, Ayan.
I mean, one obvious way that comes to mind, I do woodworking a little bit, so a lathe
Yeah.
would be an easy way to do something like that. So spinning
Yeah,
something
so
and
everybody
then,
knows what a lathe is, right?
yeah.
Lathe is something that you use friction and you use rotation. If you take an object that you rotate along one axis, you can carve out a symmetry, and then you can work through the second axis and you could make. So that would be one. Super hard to make very high curvature glass on a lathe, although glass is milled in many ways. Other ways of making. So lathe is a much more, it's a brute force approach of forcing a sphere into the universe. When does a universe give you a sphere? Yeah.
When you run water over rocks, they get super smooth.
They get smooth. So now that's a very interesting idea. And actually, I will come back to it. That's mathematically, there's a theorem called the pebble theorem, which is why are pebbles shaped the way they are? They are ultra smooth surfaces for a very simple reason, because when you have a high curvature point in a rock, it will get the highest friction. So what gets eroded is always the highest curvature point. So naturally, that's why you get smooth surfaces on pebbles. But let's start with simple. But then I think the answer is somewhere close to what you said, is what we use. But I want to go back, dig in your memories, other ways you can make a perfect sphere. Anybody can shout out. It doesn't have to be right or wrong, but you have to sort of droplet, yes. Kadrin, do you want to explain what you mean by that? See, you guys already know the answers, but you're just shy. We have to break some ice here. Kadrin, do you want to say, what do you mean?
I was just thinking, like when you have water flowing out of something and then you have a stream and you can cut into that stream. And then if you cut at the right point, the droplet could come out as a sphere.
And so, but the word droplet, does that ring a bell? Like even, didn't you see when there was a little drop he had put on the surface? It kind of sat in a hemisphere. And has anybody noticed, has all of you heard of the word surface tension? Does that mean anything to you, right?
Yeah.
So surface tension is the idea that many natural materials will try to minimize their surface area. Guess what? For any given volume, there's only one shape that literally below a certain critical length scale, all materials that want to minimize their surface area will try to be a sphere. And so if you take molten glass and you drop it in another fluid or something, it will naturally form a sphere. And I don't know how many of you have made, there are these cooking techniques that you can take gel. And do you know what it's called? It's a very decorative technique. Alginate, and they form beads, right? The beads are all spheres. And so if you can reduce the effect of gravity, you naturally get spheres. The very first large-scale telescopes, we didn't know how to polish mirrors, so we used mercury, liquid mercury, as the largest mirrors. So some of the original telescopes, the largest telescopes, now they don't do it that way because mercury is toxic. You don't want to fall into your telescope. That would be bad. But there was these giant scale, and then to make it even better, to tune the curvature, guess what would they do? Can you guess? If you're given mercury and okay, you get smooth surfaces, atomically smooth surface out of a surface of mercury. But now you want to add curvature. Can you come up with a trick? You spin it. So if you take a bucket and you spin it, you actually get these paraboloid shapes. So these telescopes used to have these crazy mechanisms that they would spin massive amount of mercury. But again, they're just using a physical idea. So the trick that why ball spheres are just so incredible, and actually you guys should all know this because Stanford holds the world record for the most spherical object ever manufactured on the planet. I don't hold that record. That's somebody in the physics department because they had to build gyroscopes for these small satellites. So if you ever go to from here to the quad, walk by the physics corridor, on the left side, they have on display 3 spheres. And it has a big plaque saying that this object is the world's most spherical object. And they also use the same technique that we use. It's so smooth that if you take that sphere and make the size of the planet Earth, the smoothness is smaller than a width of a human hair. So it's almost atomically perfect, but it's an object that you can hold, which is kind of crazy to think about. And it was necessary for them for gyroscopes because gyroscopes use this rotation to keep their orientation. And if it was not perfectly sphere, it will slowly forget where it was using the principle of angular momentum. So you guys should all watch that. And then I'll post some pictures of it. So why the first kind of an idea in thinking about, wait a second, I'm claiming we're going to do 1 micron resolution at a price point of $1. We cannot do traditional optics manufacturing. Traditional optics has 30 or so lenses that are aligned together. Literally, the objective that you see has 30 different pieces. And somebody, even till today, some of the most, every company in the world, there is a human trying to align. We haven't actually automated a way. So people align, they add the glue, they look through it, it's like, something is not right, they change, and then they hand polish. Every lens, still the last step in it actually involves hand polishing. So it's cumbersome. Of course, it costs $1,000, sometimes $10,000 for making a single objective. I'm not talking about a microscope, just the objective alone, which many of you use. So please handle them with care. They are very expensive. I mean, they are valuable. And the question was, could we build what is a cost performance trade-off? Foldscope only uses 2 surfaces. Then when Laura was in the lab, we actually tried building other ideas, building on some of these droplet polymer related work to do completely no chromatic aberrations, and they can start building complexity. So that was piece number 1, is the fact that, so now how do we make these spheres? It's actually a very simple mathematical trick, which comes back to what you said about pebbles. You take 2 flat surfaces, and if you can find any 2 flat surfaces, and you throw any shape in it, and you just grind. So 2 plates that are parallel, and you throw any shape in it and give it time, the shape that you get out is a sphere. And you can actually prove this mathematically, that it's just a matter of time. And so this is how large scale bearings, every aspects of things that require spheres are made. And of course, the resolution depends on how flat the surface, but you can make 1 flat and then you can make billions and billions. So literally what this machine does is it has very sharp, large plates, and you break glass and you throw it in there and you wait long enough and you get these perfect objects coming out. And that perfect object is what gives you the resolution that you were able to see. Then there is a couple other tricks in there, which is we had to design the apertures associated with it. And I'll kind of show you one analogy to this. I think this is just the notion of going back from a technical perspective, what needs to be done. So it's right here. The second puzzle for us was, how do you handle it? How do you control? It's a pretty small objective. I was very excited about using paper and folding. And so this is not technically origami. Ifulu, I think, yeah, you're muted. This is not origami, it's something else. Do you guys know this technique? When you are allowed, when you fold piece of paper, that is origami. But when you're allowed cuts, what is that called? Kirigami? That's correct. So that's kirigami. So this is a trick in kirigami. And then it's still a very non-trivial. I'll give you an example. If I ask you to make an object move in a particular way, just using a piece of paper, I mean, now you all folded your Foldscope and it was obvious how to fold and you got that mechanism out. But if I was to reverse that problem and say, give me this mechanism, there's no design tool out there that tells you how I should cut paper. Even for origami, there are a few design tools, but they're not functional. But you should think about this. We will spend some time around this. But that was the second trick, is to be able to ask ourselves a question that, so what Foldscope uses are called compliant mechanisms. There are 2 bridges which act as springs, and there are magnets inside that load it, so it's spring loaded. And then it's essentially using the flexure or the strain in that piece of paper to balance, because you have to control the height of the objective by microns. And then the last third mathematical trick, and then I'll give this as a reading assignment that you should all read the original Foldscope paper, is that everybody knows the paper, which is a 12, 13-page paper, so it's manageable, but there is a 30-page supplementary document. And the magic is actually in the supplementary, which is that equation right there that you see, is we had to ask ourselves a question. Very high curvature objects have a huge amount of aberrations. And so why is it that you don't see these aberrations when you saw in Foldscope? Because most of these objects only have this is called the fat lens equation. I don't know if you guys have done any optics at all? Like even in high school, you guys remember the thin lens approximation? When you say that I'm going to assume my lens is thin enough. No? Okay, so we're going to try deriving it in the next class. And then you will have to do it seems simple, is to try to find a focal length of a sphere. It's the most simplest shape that you can imagine, and it takes a little bit of thinking, but it's important to do. And kind of one of the key challenges for us was we could not use what is mathematically called the thin lens equation. You have to solve for it completely, but it's geometry, so you can solve it. So there's a lot of really fun algebra and geometry. But that led to this aperture, which is this optimal aperture. And so you notice that the Foldscope has a little black thing that it holds, like a tiny pinhole. And that is optimized for a particular dimension. And that is what makes this thing work. Because at the end of the day, so I think an important aspect of this is to be able to do the kind of technical threads that are possible. And then I'm going to talk a little bit about on the application side of the story. But first, I want to just show you data. So all of you have a Foldscope now, and in the next class, I want to see data at a quality that starts to beat this. So this is some of my images. It's from a very similar pond sample that I had found. And then what you're looking at right there that's, on the small side, the little dots that you see are single bacteria. Those are single ciliates. You're starting to see objects that are, in some of those are a micron or less. You see the little legs in there? And, kind of the perspective around this, I'm also using a trick which is called a pseudo phase illumination. You can do dark field illumination with this. You can hack your Foldscope to do fluorescence microscopy. You can do polarization microscopy. And one of the perspectives here is that once you have a core, I want you to push the limits to see the kind of quality of images you can collect. And then again, this is only on the things of what you can see. Then you add a computational layer to it, which, some applications, people have cell phones. Most of the time when I bring out a Foldscope to people, I don't bring out the phone because I'm not going to be leaving that behind. But at the end of the day, it is possible that now you can add a compute layer to it to be able to analyze all kinds of other things, add machine learning on top of that. And one thing to do is, I think the way we structured the program, and then I'm going to then transition and take questions. Around that time, when we had invented this thing, there was still this notion of, so what do we do with it? And at that time, what I decided was we are going to ship out a microscope to anybody in the world for free, anybody who asks for it. So on our website, we just wrote a two-liner saying anybody who asks for microscopes, will ship it. I was initially thinking we'll get 10 or so thousand queries. We got around 75,000 messages from people around the world. We ended up making around 100,000 microscopes in the lab. It was just me, Jim, and one more undergraduate. That's it. And how did we do that? That's robotics. So the entire pipeline of Foldscope is we could make a lens and the aperture 1 unit per 6 seconds. And so that's, you kind of think about that. Most objects that you think, the reason that pen costs that much is because behind it is a massive amount of robotics. You have to remove labor. And so we had to solve those sets of challenges. But there was a very interesting thing that I want to end this note on, is initially we were thinking we are designing a tool or an instrument. But what we ended up designing with this as an approach was actually a community. Because these 100,000 people then drove massive number of applications. So if I look back now at, I think somewhere there is an online data set. This is this is a long time ago. Now the papers have reached around 1,500 or so papers. But all of this work is done by people that I've never met, people that all we did is provide the tool. It was their ideas, their approaches, their validation, their challenges. And much of what that drives is that it kind of creates the sense of a broad community. And still today, what is very powerful in the context of this as a tool is that the community is even far more important than the tool. Because now we have been able to use this community to drive many other projects and bring new tools to the table. So, if you're thinking about a project and you're thinking about scale, one of the most important early thing you have to ask is, can you create a kind of a community that would care as much as you do, and then drive it in directions that you can't? Like, I don't have a background in soil biology, but now I work on soil problems because people reached out to us to saying, no, this tool must be used in understanding our soils from an agricultural point of view. So they bring a new angle or expertise to the table that you don't have at that time. So it's important to think about shaping. I think this will be relevant slightly later in a project, but it was a very strategic step at that time. Of course, I didn't realize that I was being strategic. You just do what you think is right. But later on, when I look back and say, oh, that was probably the most important decision that we made, that we didn't commercialize this tool in a conventional way. We first ask, let's see what the world will do with it, and then we can go back and figure out what we need to do on our end. Okay, I'm gonna stop here, but maybe I just want to show you guys some fun pictures. There is a massive number of use cases, and this week itself, we are publishing a paper to diagnose schistosomiasis, one of the disease I had told you, with this tool itself. So if you guys come by the lab, on the left side, you will see all these photographs from Nigeria, where the first field study happened. So I think this happens to be a tribal community in India related to plant diseases. So this is in agriculture, and that happens to be a fungus. And this is a massive agriculture community that primarily uses Foldscopes to diagnose diseases early in plants, but letting the farmers actually be the people that are doing this diagnosis, because they already see, oh, I have spots on my leaf. Can I just put that leaf? And immediately they know, oh, this is a fungal infection. I shouldn't just be spraying everything. I should just be curing this plant. And the earlier you do that, the earlier you have in terms of thinking about access. There's lots of threads around species discovery. I like that picture because that's the only animal that has used a microscope. That's a chicken. That's a long joke that'll take much longer time to explain. But this is really around kind of the biodiversity side of the story. And then the thing that I want to do is we will pick that in the next class is if I open a browser here, you all have this. I don't know, were you guys able to see the community site?
I sent the link.
Yeah, so I think everybody should create a link. And if I come in here, for example, these are all posts coming from around the world. And what I can do is come in and find sets of things, and you can click on a given post. I mean, very much like iNaturalist. And if I go in here, this is all data that's coming and flowing in real time. And one thing that I would like to do is for you guys to create your own accounts and start posting and spend the time looking at certain sets of things. And then that's when you will become sort of a part of a community per se, because it's also important for you to learn how to use the tool. If this is your first time doing microscopy, that's very valuable. And I think this is also true for everybody that's also in the class, because much of what happens in this is driven by having conversations with many other people that are like-minded who are thinking about these same sets of ideas. So what you will find is that the community aspect of this is very powerful. And then everybody on the site is actually equal. So you're judged by just the work that you post. But there are incredible human beings in the community who teach different skills. So to me, it's a little bit like my open science lab notebook. So every time I'll find something new, like for example, my daughter just got bitten by an octopus recently. It was a pretty scary experience. So I was able to pull out the stinger from the arm and actually share. And then I also posted, and then it turned out it was the first time anybody had seen stingers like that from an octopus. And then I also shared that post with a whole bunch of octopus biologists, and they're like, oh, we haven't seen that. But because I had a Foldscope with me right then and there, and I had to remove it anyway. And so, of course, it turned into an experience. And then she learned not to please don't pick an octopus if you see one. I mean, she knew that, but she did it anyway. And I think kind of one of the threads around this is it's you have to make it a part of your life in some sense. You have to have it have meaning. So if you're doing something and then suddenly you're cooking something and you say, "Oh, I want to look at what this is," that starts to get you going and asking yourself, are you curious enough to start looking at everything? So think of it as a tool both for learning microscopy, as an example for kind of the principles of frugal science, but also it is a very powerful tool for you to be asking questions about ideas that you can then utilize. You might observe a phenomena using a tool like this that then will become part of a project that you say, oh, this is an interesting idea that we're going to explore. Okay, I think we're out of time. I'm going to open up for questions, comments, threads. I think Foldscope will continue, but one important thing before any of you leave is just make sure that you really pushed your skills. What I do expect from all of you is not like a picture or two. I'm expecting you guys to surprise me, show me something totally new at a resolution that meets. And, for every tool, there are these learning, and then I can do a couple of sessions if people bring samples. So bring certain sets of things either before or after the class, Friday sessions. Try to push the limit for what you can do so you actually understand the capacity of a tool. Otherwise, what it ends up happening is, as any novelty, it just sits on a shelf, but you would have missed out. You have to find your own aha moment. Either it already happened on Friday for some of you, but if it hasn't happened, you have to do it for yourself, and it might not happen in a classroom. Uh, I got my first tattoo recently, and I looked at the skin cells of how the hell does ink get into the tattoo, and it was pretty cool. I kind of understood now the process that's involved because while the tattoo was healing, I could still image it. But it's not trivial to image with a Foldscope where light is not passing through. I had to change the setup to do reflected light microscopy. And so suddenly you kind of say, bring a problem to the table. This is what I want to image. Oh, maybe I want to image in the canopy of a redwood tree. How would I go about that? Yes, questions, comments, people that want to ask questions or make comments, you can just raise your hands. Yes. What was your name again?
Jesse.
Yes.
It's kind of a crazy idea. But
Yes.
where I'm from in Thailand, in local hospitals, they actually can't diagnose type 1 or type 2 diabetes because of cost. And I saw in a paper that you can actually use saliva and a microscope to diagnose that.
Yeah.
Do you think there's a possibility?
You could test it. That would be pretty straightforward. Absolutely.
Look at
Yeah.
saliva.
So what some of the papers, what Jesse is talking about is the idea that if you take saliva of a person, they have certain amount of sugar, they have certain amount of compound. The way it dries is actually quite different. So drying patterns have been used in the past. In fact, there used to be an old pregnancy test, I'm told, that from tear glands, you could actually tell the pattern in which the tear glands would dry would give rise to a hint whether this hormone is present or not. So there's all these, even how blood dries, people have used that to study and understand kind of the anemia and the degree of anemia. And then again, what microscopy does is gives you that at a degree that's deeper. So super useful, very valuable to try. And in general, what you would discover is not just humans, try finding image saliva for every animal that you can find. And there's some really big surprises. So in general, start by just imaging. You will see the most complicated. Oh, Hope. Oh, they're looking for me. Can you tell that we're hiding here? Yeah. They're gonna run away. The most complicated microbiomes exist in our mouth. And then you can compare all the animal. I just did a comparison for dogs and cats. I'll let you guess. Who do you think has a cleaner mouth, a dog or a cat?
Yeah.
No, it's the dog. The cat is the worst possible. Worse. It's natural, but it's the most highest density of bacteria I have ever seen in any biological sample has been in a saliva of a cat.
Cat bites are really bad.
Exactly. And also cats eat like all kinds of stuff. They kill all kinds of animals. And that's why you should not let your cat lick your face. So anyway, it's kind of, you have to do these personal experiences. Akshay, do you have a question? And then there's a question here. Yes.
Hi, I had a question about
And
whether.
then Akshay, can you just quick introduction so we start remembering people?
Yes, I am Akshaya. I'm a third year undergraduate student at Ashoka. I'm pursuing a degree in chemistry and biology, and I have an interest in matter in healthcare, so physics and bio. So I had a question about whether the Foldscope or Octopi and some of these other instruments have ever been used or trained by anyone in your lab to possibly look for biomarkers in blood or other samples, like say for diseases like arthritis, stroke, etc.
Yeah, I think we have done less work, I would say, on non-communicable diseases, which are very important. The first one, the two that come to mind right now is I think on the arthritis side, there was a doctor that has written a couple of papers on using Foldscope to look at these crystals that form in some of the fluids. There is some amount of work in urine to look for biomarkers to see early precursors of what might actually exist in urine as the microstones that exist often enough. I've done a little bit of work looking at cough. There happens to actually be in human cough, there is an oxalate crystal. I don't know how many of you guys know this, but you can cough needles, glass needles. So if you take a cough, if you have a really bad cough and put it in and you image it, you'll find these, if you have a particular condition, these very, very fine glass needles. So I would say, Akshay, the most of the threads are precursors. I think with Octopi, there is a large number of data sets we have now that are going down in the direction of hematology. And I think maybe one comment I would make is think of these as complementary tools. Octopi is still a lab bench-based device. You know, you will see it. It's a kind of a larger instrument. It's all automated. It has many kinds of modalities of imaging, and it does very fast imaging. It has AI, while Foldscope is something you carry in your pocket. And these has complementary utilizations in terms of where you physically are and at what conditions and at what price point. So I often think of Foldscope as a screening tool and then Octopi as a diagnostic tool. And even for schistosomiasis, we're starting to do these early screenings because in an early screen, you can still treat people because right now they're already doing mass drug administration. And so it allows people to understand which villages they should be doing a mass drug administration to begin with. So when it's about extreme portability, then it's valuable to build on top of a Foldscope. If it is about inside the lab and really matching the same kind of conditions of imaging that you would get in a lab at Stanford, then I would build on Octopi. Okay, there's a question in the class, and then Ayan, I don't know if your hand is new or old, and then Honey also has her hand up. Yes.
Yeah. So
And can you say your name one more time?
I'm Luke.
Luke. And then you sent me a message. Yeah.
Yeah, I'm a Stanford senior.
Yeah.
I'm just curious, like, what's like and I probably can search this up and find the information, but what's like the scale of the full scope? Because I can imagine there's different problems where you need microscope for like unicellular organisms.
Yeah.
Versus like you need maybe like for microplastics, you need like bigger scale.
Yeah.
Like something on the skin, you need
Yeah.
scale. So is there a scalability for the kind of like focus of
Yeah, I think kind of one of the threads to think a little bit about is Foldscope is much more of a platform. Lots of applications get built on it, but then we also build very application specific instruments. So for microplastics, for the survey, because Foldscope is manual and it can handle samples, but only one at a time. And so when high throughput was needed, then we actually built Planktoscope that now has become its own platform. So it's seeded all these other projects that now. So you can start somewhere and then you can also learn the limitations of a tool and say, oh, I get this. Now I want to add automation and I'm okay to jump the cost. And so what I said, like this remains at $1. There are instruments that we built that are $10. There are instruments that we built that labor like $100, $1,000. So it's organic. And I think what I'm trying to say is when you start working on a problem, you want a starting point, and then you might go back and forth. You might also start at a starting point that's overpriced, and then you retract and you go back. I'm going to remove the features because what you're trying to do is what you don't need. I mean, I think in terms of the total numbers, one of the important thing that matters is this is in the original paper, we describe many different types of imaging that is not implemented in the tool that's widely available now because we don't manufacture some of the we build zirconium lenses to do this very, very high resolution imaging with a Foldscope. But then at that time, it didn't make sense for that particular application. So we don't manufacture it, but all those capabilities are also still there. But think of it as an organic approach to arriving at your price point or your sets of solutions too. But I also like the idea of getting started quickly so you get a sense that, oh, whether this will crack the problem. For Schisto, for example, when the first 2013, we did a clinical study to do full scope diagnostics for schistosomiasis. And we had decent results. Maybe I would say 70% specificity sensitivity, and I wasn't so happy. But 10 years later, we visited the same question and we included another technical advantage, which was a type of a filter, like a schisto filter. And that now suddenly has jumped the sensitivity to 90%. So it was another component that was missing in the early phase. That's another way of thinking about it. Honey, go ahead. You had a comment/question.
Yeah, so my name is Hani Yadav. I'm working as a postdoctoral at Birmingham City University. Presently, we are trying to utilize solar energy to solve a problem in Bangladesh. To be specific, I wanted to ask that can we use it to identify waterborne diseases? Because we saw a graving problem that is emerging of water pollution in Bangladesh because of apparel industries, a lot of agriculture practices. There are high pesticides and heavy metal presence. So, and there is low awareness. So basically, I wanted to correlate that how we can utilize this as awareness making tool from that perspective. Yeah.
Yeah, so I think a quick thing, there are two aspects to it. One is we have worked with a couple of projects in Tanzania around the WASH protocols. That's on the awareness side. And so there's a lot of documentation. That would be a pretty straightforward. So a WASH protocol is by WHO to build programs around sanitation and hygiene. I mean,
Sanitation, hygiene. Yeah. Yeah. Sorry.
the idea that you should wash your hands, but then many a times they would go to schools and sing songs that, oh, you have microbes on your hands. Like, what does that mean? Or you can show people what is in the water and what's in the hand and what's in the soil, and thinking a lot more about how behavior changes. So that's one aspect to it. But the other one that I would be excited if somebody wants to pick that as a project is really building a kit for water quality testing. And I think water quality testing has been on our priority for some time. We haven't as yet
Yes.
picked that up. There is a large number of kind of usually tests that are done in more on the chemical side of the story, but there is a lot more that needs to be done on the biological front.
Yeah.
And then there are these secondary methods too, that you could do one step that's chemistry, but then the readout of that precipitate that you got could be microscopy. So
Yeah.
think of it this way, that you let chemistry do half the work and then you let optics do
Yeah.
the other half. Rather than often enough, like many of the assays that people build that are read by eye. I mean, an RDT is a great example. Chemistry does all the work. But last year, there was actually a student that implemented some of these imaging techniques inside an RDT to improve the resolution of what you can detect in the RDT or make the RDT multiplex for that matter. So think about that way. I think water we can talk quite a lot about, but I think there is a couple of times that we have touched upon it. But if we was to say, given a water well, prove and demonstrate whether this is safe to drink, that would
Yeah.
actually require a higher bar that we should pick
Okay.
stuff up. Yeah. Okay, two more questions. And then what was your name again?
Nick.
Yes.
I was wondering because it takes a lot of iterations to do it. I was wondering when you realized it was the right time to deploy, because I imagine you were probably already thinking, oh, this is a limitation, we could keep improving it. Was it once the cost was like below $1, or when did you realize?
Yeah, I think I have an approach that I deploy even before I have built by starting to talk to people what we are building. You should always deploy because we're deploying in research communities. We're not, so the first time you want users to see is even before you are done. And it feels very awkward. It's very embarrassing. Everything falls apart. But we were out there all the time, just sharing what we have, knowing fully well what we can solve technically, and giving that honest indication. But you cannot wait to deploy. If you wait to deploy, it's already too late. I mean, people say this in software, but it's actually really true in these types of projects because you grow with every time we take the tool out. And many students every month, I mean, Lisa is in Ghana right now, and people are out there from the lab because we need to be able to show. And once we can show people something, our own thinking about what needs to be done changes. So it's not, you don't get to decide whether it's good enough. You let others decide and like let that conversation happen. And I think there's something quite organic about it. Yeah.
There's a quote in the Silicon Valley.
Yeah.
It is, ship fast, fix later.
Yeah. I think I like the idea of, there is also an aha moment that you share something that should generate excitement in people. So you should prepare, but it is true that you want to ship fast. Okay, last comment from Ian, and then I have to run.
Hi, you had mentioned like these two sort of threads of thinking, where you could either like sort of look at systems or mechanisms and like study them out of curiosity, and like you could have a sort of an understanding of a system, but not necessarily know what kind of a problem it might solve. And then you could also be looking at problems and trying to find a solution to that. So I was wondering, since all of us are sort of trying to work towards a project, could we sort of crowdsource ideas on both of these things and then look at everybody's ideas, and like maybe something that I'm thinking of might solve a problem that somebody else wants, or
I love that. I love that. And I think, and on one side, we have this on Notion and now in this wiki, we call it the idea board. And the idea board is really for problems. But what you're just suggesting is what I would love to do is let's build another equivalent board, which is the world of cool, fun things. What I mean, like what I said, that there is a mathematical way that you can make a sphere. Let's come up with all possible things like that that just exist, that our nature gives us to begin with.
Exactly.
And it would be phenomenal to document. I mean, this is why I love reading papers, and you should all read extensively. And that space is infinite. Like, I mean, it's literally infinite. You might say, oh, Brownian motion, just how these particles move. And then suddenly you could ask yourself a question, how would I use that particular
like
thing that nature gives
while
you?
you were speaking about Kirigami, I had the thought of how I mean, there's this guy Eric Demain at MIT, and he has done some work about how you can sort of take any 3D model and like turn it into a flat foldable 2D model. And now
Yeah.
that is something that you might not know what kind of a problem it might solve, but if somebody has a really great idea for something that's 3D and they're looking for a way to flatten it, you could now
Yeah.
take that sort of a tool and
Yeah,
put it
and I
there.
think some of the design tools that are now being used in telescopes and others have come from some of the theoretical ideas that people have worked in origami for the longest period of time. I think one of the things, it's fantastic for us to document. The one important thing I want to mention is that that is literally what we are talking about, is documenting our universe, because that everything in nature happens in a certain kind of a particular way, and it's useful to build a massive repository of knowledge, but it truly is infinite. So don't, I think, for any interest that you have, everybody should just try to pool that together, and it'll be a really fun read. So let's make I'll think a little bit about structuring it. Maybe we'll kind of do it in physics domain, biological insights, mathematical insights, design insights, and those are just for people to grab and use. And I mean, some of the course, I will cover them. So the reason I cover optics, I cover compliant mechanism design, we cover origami, is to give you a hint of what's possible. I'll do a little bit of theory for fluids. So you should think of it that every domain you're interested in are hidden these nuggets that you should be able to utilize. And then, do you know, Enrique, should we do the wiki itself, or right? Let's talk through it. Yeah, because that might be a useful thing if we don't want to pay Notion. Yeah. And finally, I am on Notion. I figured out how to configure it. So I saw all the messages. So if you have sets of questions and ideas, if you're already thinking about a theme, try creating sub channels. I think people can create channels, right? Or you. Okay, so just ping Enrico if you want a channel. So and for example, Discord is a quick way. So just create a channel around this of the wonders of nature or whatever you want to call it, and then start documenting some of those threads. And then create a Foldscope channel. I want to see the kinds of things that all of you would discover. And this week, we're going to try to make sure we can ship. I think you should just send that message to Shama. And I will go through the list to see how many we're shipping per site. Yeah. Bye, everyone. We'll see each other
Thank you.
on